Hey everyone, welcome to day 22 of Advent of Code 2022. In this video, I'll be explaining the puzzle, monkey map, and walking through all of my solutions and thought process and all of that. You'll get to see mostly a high-level overview of my solution because today's puzzles were more tedious in my opinion, less like algorithm tedious and more like implementation tedious, like lots of off by one things and just getting a lot of data sorted and rules. We can see from the leaderboard it was a more difficult day today. So I should be looking at day 22. Congratulations to Derek for getting rank 7. But yeah, comparable to days 16 and 17 in difficulty, it was a pretty difficult day today. So I'll be going into less detail, more of a high-level overview. But first, if you want to check out my code, that's going to be linked in the description, as always. And we're going to start off with a time lapse of me solving the puzzles. Alright, so for today's puzzle, we are asked to simulate path navigation on a grid because the monkeys have given us a map according to our GPS or Grove positioning system, and they want us to figure out a passcode which involves navigating around on a two-dimensional map. So the map is given as this 2D grid in this sort of ASCII art style, and then we're given a series of instructions which consists of either numbers or turns. So numbers essentially mean we should move in a direction, and turning means we should change our direction. We start out in this top left square, so the leftmost square in the topmost row facing right, and then we either move or we turn in the steps that are given. There are a couple of walls, so if we run into walls, then we should stop the instruction. And if we ever go to like run off one end of the map, then we should wrap around to the other side. So in this column or in this row, if we are in the last square and we move to the right, then we should wrap around to this square. Similarly for the columns, if we're in this column over here and we move down from this square, then we should wrap around to the other side up top. If we wrap around and we hit a square, then we should... Okay, so the point is that we start here, we know what instructions we have to execute, we just execute them, simulate them, and then figure out our ending location. So to extract the answer, the passcode is 1000 times our row, plus 4 times our column, plus the direction, which is 0 for right, 1 for down, 2 for left, and 3 for up. And this is going to give us an answer that we can input. Do note that row and column are one index. So part 1 is relatively straightforward. I got this one, I mean, maybe I already talked about this in the intro. I haven't filmed it yet, but I got rank 1000, 1 hour, so, not terrible, because today's puzzle was pretty difficult. Anyways, for part 1, it's a little bit simpler. I'm not going to go into too much detail about this because there's just a lot of code and it's kind of tedious. But the idea is pretty simple. We maintain our location in this row and column variables as well as our direction, and then we just update them according to the instructions. So whenever we get a left or a right, then we can update our direction variable, and whenever we get a number, we should try stepping in that direction. So the bulk of this is just figuring out when to when to wrap around, because knowing when we hit obstacles or walls and changing our location, that sort of update stuff is pretty straightforward. So the difficult part is figuring out when to wrap. So when we wrap, we are either hitting the left or the right most squares in a row, or we are hitting the topmost or bottommost squares in a column. So I'm actually going to do a little bit of a diagram for this. This is what the map kind of looks like in the sample inputs. And so, for example, if we're over here in this square and we wrap around to the other side, we should end up over here. And the actual thing that's going on here is this current row has a range of columns that are allowed. So for example, this might be column 8 to column 11. And if we try to go to column 12, then we should actually wrap around and go to column 8. So in this example, the bounds of the columns are 8 to 11. And then if we try to go to 12, this should bring us back to 8. We can kind of generalize this. So for example, if we're in this column and the rows go from 0 to, let's say, like 15, or actually this should be 11 as well. So the range of available rows in this column is 0 to 11, and if we try to go to 12, then we should wrap back around to 0. And the idea here is that we can use modulos. So if we have a range of places that we can go, and we try to step outside those bounds, then we can use mods to cleverly wrap around. And the idea is that, for example, let's just say we're moving vertically. So we have a new row given our current row, and we know that it oversteps our bounds, or it doesn't even have to overstep our bounds. What we do is we take our new row. So let's say we're trying to move down, and this is the range of allowed values. And we're currently at new row. New row is outside of this range. It's like over here in this little slot. Then what we're going to do is we're going to take this and subtract it from the start, which gives us a sort of length here. And we're going to take that, mod the length of this whole allowed region, and that's going to bring us back to 1. So for example, if the length of this allowed region was 10, 10 allowed squares inside this column, that's the row range, then maybe let's say this is coordinate like 13 and start is at 5. Actually, that's not a good example. Let's say start is equal to 2. Then we know that we are currently 11 over the starting coordinate. Take that mod 10, we get 1, and then we wrap back around. Maybe that's not the most accurate example, but it shows the point. I'm only trying to do a high level overview here again. And as we're parsing this big string, we keep track of where we're at in terms of rows and columns. And then whenever we hit like a square that's inside this grid, whether it be a wall or an open square, then we can record the bounds of the current row. So take the column and min-max it with the current row's bounds. And similarly do it for the column. When we hit a column, then we just take that column's bounds and min-max it with the current row to stretch it. There are better ways of doing this. I mean, this could be made more efficient, but generally Advent of Code has small inputs, so we don't need to worry about efficiency that much. Okay, so that's how I did part 1. A couple things to note here. You can check out my code in the description again as a reminder if you ever want to see the details, but what I'm doing here is I'm keeping track of directions in terms of 0, 1, 2, 3, 4. So this just makes it easier to do the left and right processing. So this direction is going to be 0, that's going to be 1, that's going to be 2, and that's going to be 3. And the vectors associated with these are 0 is going to be 0, 1. So moving to the right, we increase our column by 1. 1 is 1, 0, so increasing our row by 1, moving down. 2 is 0, -1, and 3 is -1, 0. So I actually messed up on this on part 1, and I typoed this. Instead of typing -1, 0 for moving up, I typed like 0, 1 to move right, which is totally incorrect, and that cost me a couple of minutes. So I guess a lesson for the future is just to keep track of this array whenever I'm using it, because this sort of like differential for the neighbors, adjacent neighbors for rook adjacency in a grid comes up pretty often. Okay, so even though part 1 took me an hour, part 2 was what really got me stuck. So let's take a look at part 2. It turns out that when we actually like approach this thing, when we actually try to get the passcode, because this was just the map that the monkeys gave us, which is still pretty helpful, it turns out that it's actually a cube. So the map that the monkeys gave us is going to fold up into a cube, so this turns into a 3-dimensional problem. And whenever we walk off one side, instead of just wrapping around to the other side like directly, we wrap around to the same point on the cube. So if you can kind of imagine a cube, I'm going to draw a 4x4 cube here. Oh no, I'm drawing over what I had previously. But you can sort of imagine walking over an edge. You're going to step over onto an adjacent face. So let's take a look at this. Let's just draw a 3x3 cube for now. And let's take a look at the front face. So if we're at the top center square here, if we're currently here, and we're trying to move upwards, then we're going to move upwards into this square. And you can kind of imagine if you unfold this so that the top faces like this, and maybe like the middle faces like this, and then you have something like that. This might not be the best diagram, but let's say like the front face is here and the top face is here. Then the monkey map is going to be divided up like this, and this x is right here, and that x is right here. There's probably a better example here to do to show wrapping, so I'm actually going to try to draw an alternate net. Instead of that, we could instead have this. That would be a valid net. Let me just draw more. Okay, I'm going to actually use different colors. So let's say this square, I'm just going to color it in now, is red, and we're moving upwards into this blue square. On the net, it might look like this. So the red square is going to be over here in the center, while the blue square is all the way over here. So when we're wrapping around, instead of just wrapping around to the other side, we need to consider the net structure, how it folds into a cube, and it actually wraps around over there. We also need to be sure to change our direction. So instead of on the monkey map continuing to move upwards, we need to now start moving left because that's the straight line on the cube. Okay, so understanding this might take a bit of time, and there's more challenges, which is actually implementing this in code. So the input, I guess, gives a good example, but drawing a 3D picture really helped for me. The idea here is to not write a bunch of like conditionals to do this mapping for us, but instead to write an automatic function to determine what wrappings should occur. So let's take a look at the sample input here. I have some scratch paper that has my work on it. It looks like this. This is the sample inputs. I'm gonna just draw it out real quick here. Might not be the best diagram, but you know, it's a speedy one. Okay, what we first have to do is to actually figure out the net structure of this thing. So we know that there is a coordinate system, and instead of actually using the rows and the columns present in the monkey map, I'm just going to use simpler coordinates. So instead of going from like 0 to, what was it, like 16, I'm going to go from 0 to 4, so scaling everything down by the side length of each of the faces of the cube. Thanks to Derek for suggesting this. I think this sped up my map encoding a lot. So you can see, like, eventually in part 2, we're going to have this thing, which describes all of the edges that map together in the net. But let's just see how this works. So how I did this was, you kind of have to have some 3D visualization skills for this. But let's say we have an edge here, A. This is going to map to the edge. Let's see, it's going to map to some other edge. Let's see, it's going to map to this edge over here. And the direction actually matters. So this edge is currently pointing to the right. It's going to map to this edge that's pointing to the left. And I realize blue is a really low contrast color, so I'm going to rewrite this in white. And these two edges map together because if you can imagine this cube folding up towards us, that top face is going to come out of the screen, and this left face is going to fold up and then over. So eventually it's going to be covering this middle square, but like up a layer. So if you can imagine that, then this top edge over here will coincide with this edge, and the directions that they're overlapping in will be like kind of opposite on the 2D map. So you can kind of imagine, I guess you can't really see my hands that well, but that edge is going to come over and flip over and be over this edge protruding from the screen 1 unit, and that's going to be exactly where that ends up. So that's sort of the idea behind matching up these edges. To actually represent this in code, we're going to say the edge over here, which is represented by the vertices 0, 2 to 0, 3, and we're actually going to make a note of its direction. So going outwards, it is pointing up. And the edge from 1, 1 to 1, 0, pointing up, these two are going to coincide. And the order actually matters here, because consider that that we might be going from this point. Actually, I probably shouldn't be using blue. Going from this point upwards, we're actually going to map to this point over here and start moving downwards instead of this point and moving downwards. So you can see that the red point is closer to the starting vertex of this edge. So it needs to preserve that property when we wrap around. Anyways, inside this sample case, 0, 2, 0, 3, again, this is row column. This is my sample file. We can see that 0, 2, 0, 3, this edge, that top edge over there labeled with the first A and pointing upwards, coincides with 1, 1 to 1, 0, which is this left edge that is also labeled with A and also pointing upwards. So eventually we can do this for all of the edges, and this is just the sample input again. So for example, this edge B, if we sort of do some more visualization, we can find that it lines up with this edge on the bottom right, also labeled B. You can kind of imagine this one like sticks out vertically from here going upwards out of the screen, and this one, when you like fold it over, it does the same thing, and the directions also match up. So this is going to be from 0, 3 to 1, 3, pointing to the right, so that's the outward direction. This is going to coincide with 3, 4, mapping to 2, 4, also pointing to the right. So their directions do matter here, and you can see 0, 3, 1, 3 pointing to the right maps to 3, 4, 2, 4 mapping to the right. And we repeat this for all 14 edges. And it turns out for any cube net or any like convex cube net, there are going to be 7 of these pairs, so 14 edges in total, which is, it took me a few minutes. Anyways, I can't generate this automatically given the input. That's just going to take too long. I don't even know the algorithm for doing that. I mean, I could probably figure it out, but it would take a while. So if you're going to try running this code on your own input, you do have to do it manually. I'll include some kind of disclaimer in the README to assist in that. Okay, so there's a lot of code here, and there's a lot of edge cases, and dealing with all of them is going to be a pain. So I'm just going to go over it briefly and kind of show you around what functions I used, what methods I used to assist. So first of all, we have all of these functions, which kind of just are me avoiding using NumPy. This is the add function. It takes 2 coordinates and it adds them together, or like 2 vectors and adds them together, pretty basic. This is the multiply function. It takes in a vector, multiplies it by a scalar. We'll see that this comes in handy much later. This is called normx, which isn't really right, but basically it returns the sign. Maybe I should replace this with a sign instead, and that'd be more accurate. Okay, anyways, when we have this edge map, this is a pretty human readable format. We have start vertex, end vertex, that's one edge, and then the direction of that edge pointing outwards again, and then we have the ending start vertex, the second edge's start vertex, end vertex, and then the direction which points outwards. Parsing this into a machine-readable format is going to be a little bit more difficult, but it's not that hard. Basically, all we have to do is first turn these strings, which very clearly show up, right, down, and left, into numbers. So again, that's going to be 0, 1, 2, 3, 4 over here. And parsing that's not too difficult. We can just use a string index function in Python. Next, we have to turn these coordinates into actual coordinates. So the scale here is 50 to 1 because remember, again, we are not using the actual coordinates here. We are scaling everything down so that a side length of the cube has length 1. Now we have to scale it back up to get actual coordinates that are going to be helpful for the wrap function. So the crux of this is really the wrapping function. It takes in a coordinate that we're trying to move to, and it wraps us around to the other side if applicable. So it detects, first of all, if we're on an edge, or like if we've just crossed an edge. If so, then it finds the matching edge, wraps us around to that point using the index that we're currently at along this edge. So as an example, over here again, if it detects that we are trying to walk off to this point that I've highlighted here in, let's say, green, then it's going to wrap us around and return us to this point, which is on the inside. And it does that by, first of all, going through all of the edges, looking at where we're at, finding the index along this path. So in this case, that's going to be a pretty short amount, and then finding the corresponding edge, moving along that edge by the same amount. That's a really high level overview. Let's dig into a little bit more of the details, not too much though. So the idea is that we have this edge map. Now all of its maps from, now all of it is describing big coordinates. So in our example, this edge is no longer going to be 0, 2 to 0, 3. It's going to be like 0, 4 to 0, 8. Or rather 0, 8 to 0, 12. The utility function that we're going to use here is called offEdge, which is going to take in an edge, take in a point, a direction, and tell us if that point has just walked off the edge. So let's take a look at offEdge. Again, it answers the question, did we just walk off this edge? And if so, it returns the index. So edge is going to be start vertex, end vertex, direction of the edge. And we're giving it a point and the direction the point has just moved in. If the edge direction and the point direction do not align, then we cannot possibly have walked off this edge. Again, remember that edge records the direction that points outwards. So we need to check if we have walked like outside this edge and into the abyss away from the net. So if those two directions don't match, then we can just say, no, this point has not walked off this edge. Otherwise, we do need to do a bit of like off by 1 correcting stuff, because when we're scaling out, for example, let's say, let's take a look at this example again. It's kind of messy now, but I'll clean it up a little bit. This edge now goes from 4, 0 to 8, 0. 0, 4 to 0, 8, or rather 0, 8 to 0, 12. I don't know why I keep making that mistake, but what we actually want to check for is if the row is -1, because if the row is still 0, then we're still within the bounds and we don't have to wrap anything. If the row is -1, on the other hand, then we do need to actually wrap to the other side. So if the edge is pointing upwards or it's pointing to the left, then we have an off by 1 error, and we just need to subtract some stuff, add some stuff. That's not too important. We can ignore that for now. This off by one thing will come back later though when we're plugging back into the other edge, so do keep it in mind. And then you can see I wrote a comment here, which is basically saying that we can just check from the start vertex to the end vertex. I don't know why I wrote edge here. And just check if that point matches the, like, any points along the start vertex to the end vertex. So what we do is we get the vector that points along this edge direction. Remember, this is not the direction of the edge, which we defined as the direction that points outwards. That's one of the vectors, 1, 0, 0, 1, etc. This is going to be one of those vectors, but it's going to point along the edge so that we can actually iterate along its points. Or rather, just a 50 length edge. Checking for 50 things isn't too hard. I don't think this will introduce like too much of a slowdown. But yeah, we just iterate along this edge, check if any of those points equals the input point. If so, then we have just walked off the border. So this loop is going to check everything along the outside of this edge. If we're looking at this edge, then it's going to check all of the points along here. If it's this edge, then it's going to check all the points along here and just return if those have contain the input point. Okay, so now we have a function that can take in a point, take in an edge, take in a direction that the point has just moved in, and return the index along this edge that the point has just walked off of, if applicable. If not, it returns none. So now this is great. We can just look at all of the edges, all 14 of them. Look at our current location. So we're going back to the wrap function now. Look at our current location, see if we've walked off that edge. If so, then we need to find the matching edge, and then move along that by the index that we were at in the edge that we just walked off of. So there's a bit of code here. Since the edges are commutative, like walking off one edge and going to the other edge is the same as walking off the other edge and going off to the first edge. This is kind of the benefit of writing the edge map in a like paired up sequence like this. We don't have to do redundant things. We're mapping like A to B, or like A to B might be a bad example, but like edge 1 to edge 2 and then writing edge 2 to edge 1, we could just combine those in the same pair in this list, which reduces the computation for us. So we just have to do a simple check, do 2 checks here instead of 1. But yeah, we look at both the edges, see if the point has walked off that edge, and like mix and match to make them equal. So if they're not in the right order, then we just swap them around. And now we have E1, the edge that we just walked off of, E2, the corresponding edge, which is actually the same in the cube that we should walk to. And we also have the index along the current edge that we just walked off of. So we can map that now to the second edge using this point at function. So let's go to the point at function. This is pretty standard. What we need to do is get the edge that we're trying to map to, the index that we are trying to go within inside this edge. Basically, we just add like the amounts that we're trying to move along times the direction of the actual edge, which we get using this along edge direction, which is the direction along the current edge. I'm not going to talk about the function because it's pretty simple. But yeah, just move along index units along this current edge and just return that. We do have a little off by one error here, which is the same one that popped up previously. Now, instead of being a top or a left edge that we need to adjust, it's a right or bottom edge. So for example, if we're looping, we're wrapping around to this edge, we need to wrap on the inside. So the points that are actually described by these endpoints are going to be something like 8, 12 and 11, 12. Well, actually what we want, sorry, this is not correct. This is 8, 8 and 8, 11. What we actually want is something with row number 7, not row number 8, because we're going to on the inside now. We maintained this when we were checking if we walked off an edge, because row 8 describes the outside. Now we need to go to the inside. So if the direction is 0 or 1, which are the right or bottom directions, then we need to adjust our edge for the off by 1 error. And yeah, that's the point at function, pretty standard. Find the indexed points along an edge. Okay, so now going back to the wrap function, we have figured out the point that we should wrap our location to, if applicable. So we can just return that. But one small modification is we do have to take note of the new direction that we're traveling in. So thankfully, finding the new direction isn't very difficult because we already know the edge that we're traveling to, and the edge that we're traveling to, we know its direction because we wrote it down here. So we do have to flip that direction around because the direction points outwards. We just need to point it inwards now. Flipping it around, that's what this line is for. Okay, I think I covered all of the points I wanted to cover in these utility functions, so let's actually go to the main function. So we're going to do the same thing pretty much as part 1, except now instead of checking for if we're outside some row and column bounds, and wrapping those around, we're going to use the function. So this function is going to return a new point that a out of bounds point should wrap to, or if it's in bounds, then it just returns the identity. So after we try moving to a new point, new row and new col, we're going to store the row and column that we're trying to move to. We try to wrap those around and throw those in new col and new col row. If we have decided that this new row and new column location is a wall, then we should not wrap and we should stop our movement. But otherwise, we can continue our movement and just reassign and keep going. So it's the same thing as part 1, except we use our handy dandy function to do the wrapping for us. Okay, so that's it for part 2. It's kind of a more complicated puzzle because it involves 3D things. But in general, I would say this is less of a algorithms heavy puzzle and more of a program structuring and efficient coding puzzle. I am glad that once I debugged all of my code on the sample input, it actually worked on the test case input, or like the actual input, because like debugging your code on a sample and then not having it work on the actual input is very frustrating because you don't know where the bug is. Anyways, again, I did a pretty high level overview of my solution and thought process because I thought that'd be the most valuable. Going into the detail about the code and all of that probably would have taken too long and not been super informative. But if you do want to see my code, it's going to be linked in the description below. Be sure to check that out. It contains my solutions to all previous days of AOC 2022, except for 16 and 17. I haven't finished those yet, but they will be coming soon. I did finish day 19. I'll make a video about it soon. I ended up running a script for about an hour overnight. Somehow it worked. So anyways, hope today's video was explanatory for day 22. If you have any questions, comments, or feedback, feel free to leave that down below. I will take a look. And that's it. Thank you for watching, and I'll see you tomorrow for day 23.